So today we will proceed into the discussion on multipliers. Okay, so in this class I will just cover the basics of what the multipliers are, what these terminologies are, and I'll also go into the 2's complement number representation, right? So how many of you are already aware of 2's complement arithmetic? Not 2's complement representation, I mean 2's complement arithmetic, right? When you do a multiplication, what should you do and all that. So have you worked out the math of why, for example, sign extension will retain the value? Yeah? You guys? You have not worked out that math. So that we will do in this class so that you get a hang of the mathematics also behind it, so that we are perfectly consistent with what we are doing in the rest of the module. Okay, so fine. So I have x, which is, let's say, an m bit number. Okay, and y, which is an n bit number. And I am going to assume that both these numbers are unsigned. What does this mean? It means that x can be written as xi to power I, where I goes from 0 to m minus 1. Similarly, y can be written as j going from 0 to n minus 1, yj to power j. So I am now going to create a product of these two numbers, and this will be x times y. So if x is m bits and y is n bits, how many bits will z be? So we'll look at that. So this is I equals 0 to m minus 1 xi to power I into j equal to 0 to n minus 1 yj to power j. This can simply be written as I going from 0 to m minus 1, j going from 0 to n minus 1, xi yj into 2 power I plus j. And I am now going to write this as a product zk to power k. K is going to go from 0. So if you take the 0, I equal to 0, j equal to 0, right? Clearly I plus j will also be 0 there. So it starts from 0. And what will be the maximum value? M plus n minus 2. But you will find that there is also a carry that comes because you are doing an addition, and you could get at most one extra bit there. So this will become m plus n minus 1 z power k. Okay. So what is this coefficient z power k? This is equal to summation of xi yj such that I plus j equals k. So you are just grouping all the terms and you are able to evaluate the coefficient of 2 power k. Okay. So let's look at a simple example. A3, A2, A1, A0 times B2, B1, B0. Okay, so my x is, or let me keep the notation consistent, x3, x2, x1, x0, y2, y1, y0. Okay, so what do you get here? The first term will be x3, y0, x2, y0, x1 y0 and x0 y0. What's the second term? It's basically just a shifted thing, right? You have to shift this term by 1 bit and add. It's a shifting and adding process that we have to do here. So this is exactly like how we do normal multiplication, right? So this will be x1 y0. Oh, sorry. x1 y0. No. I need to do x0 into y1, right? So that is x0 y1, right? And then x1 y1, x2 y2, x3 y3. The last term is x3 y1. I'm sorry. x0 y2, right? And x1 y2, x2 y2, x3 y3, y2, sorry. Okay, so what you notice here is this is going to be my z0, z1, z2, z3, z4, z5, and in doing the addition of x3 y1 x2 y2 you could get a carry, and that could generate a carry and you will get z6. Clear? Now what do you notice here? This 2 is nothing but addition of all the terms whose product is such that I plus j is 2. If you look at the x2 y0, x1 y1, x0 y2, it's basically the sum is always 2. Right? That's how we grouped it in the earlier summation as well. Clear? So what we notice here is, let me get this terminology right. I always get confused with this. This is called the multiplicand. This is the multiplicand, and this is the multiplier. And in the process, you generate what is known as partial products. These are essentially partial products. Okay, so this is PP0, PP1 and PP2. So if x is m bits and n and y is n bits, how many partial products will I have? Yeah, n, right? Basically as many as there are bits in y, as many as there are bits in the multiplier, right? So this is basically, you will have n partial products. Okay, let me call it PP. Right? And what is the size of each partial product? m bits, sorry, and each will be m bits long. So in order to perform multiplication, you need to do the following tasks. One is partial product generation. Okay? Then you need to do partial product accumulation, or let me put one more term there, partial product shifting. You got to shift and add, right? This is one more operation that needs to be done. What is this? Third operation is partial product accumulation. in order to speed up the multiplier, you need to speed up all of these operations in order to get better performance. Okay, so there is also one more operation that needs to be performed, that's called the final vector addition. You will see why that needs to be done when we look at a actual implementation using full adders. Okay, so for partial product generation, what do you think is the logic operation that needs to be performed? AND, right? So this is nothing but a AND gate. What about partial product shifting? Yeah? Yeah, so this is a slightly tricky thing, and not tricky actually, it's actually very trivial once you implement it and see. As you say, yeah, if you want to do left shift, you have to move everything by this thing, but that can be simply achieved by wiring. Okay, so let's come to the next thing. What do you need in order to do partial product accumulation? You need an array of full adders. We have to arrange this so that we can perform this operation here, right? This, you clearly see there is an array of terms that need to be added in a particular way, and you need to provide as many full adders as needed to perform these many additions there, right? So this is nothing but an array of full adders. Now once you provide an array, it turns out that the previous operation of partial product shifting is very trivially achieved by simply wiring. Okay, you don't have to do, in the sense, all you have to do is ensure x1 y0 gets added to x0 y1. So if you just wire it correctly, you will find that that shifting operation is already done very easily. Okay, this final vector addition we will come to later, because it's not evident from this figure here. Okay, so we'll look at it later. And this is where your architecture of these other adders come into picture. This previous one, partial product accumulation, can be done using a typical ripple adder. Just a full adder, you ripple it through, do it nicely, you will get it. Okay, but this final vector addition, if you put a ripple adder, it will kill your delay. So here you have to use some fast adder architecture. And this is where I am suggesting that you use something like a carry look ahead adder to speed up your multiplication. Okay, now what we discussed was only for unsigned numbers. Yeah, we will come to it when I show you the implementation using full adders. You will find that there is one final addition that needs to be done. Okay, in the sense, you put these arrays together. Okay, put enough number of full adders. Suppose you are doing 4 cross 4 multiplication. You put 16 full adders in this so that you can do this addition appropriately, multiplication addition appropriately. You will find that the last stage just turns out to be a ripple adder. If you just put full adders, that last stage is just like a ripple adder. You can speed up that process by making that a faster, more intelligent adder, is all I am saying. One of the last row in the array happens to be a ripple adder. Other things are not ripple adders. They are full adders, but it's not a ripple adder. Okay, we will see why. Yeah. Actually, in reality, if you look at a microprocessor, nobody cares if you are doing 4-bit into 3-bit. Everything will be converted into 4-bit into 4-bit. You append zeros and proceed. Right? That's all. So this N and M is only to tell you, just tell you which one is giving rise to more partial products, which one is giving rise to, that kind of thing. No, that's why I said if you are doing x into y like this, then number of partial products will be this, right? If you do it the other way, then yeah, you'll have more partial products. Okay, this is the convention I'm saying. M is x is m bits, y is n bits. Okay. Okay. So unfortunately, what we did earlier was just unsigned numbers. That's very clear. So we have to also deal with signed numbers. Okay. So I want to represent negative numbers, and therefore the most obvious thing to do is to assign that most significant bit to a signed bit. If it is 1, the most trivial way of doing it is, if that bit is 1, it's treated as a negative number, the remaining n minus 1 bits as a negative number, or treat it as a positive number. Problem with this is the 0 happens to have 2 assignments, plus 0, minus 0, which is useless, and therefore people move to this thing of 2's complement. Representation. Two's complement representation is, I have an n bit number, a n minus 1, a n minus 2, all the way to a naught. Right? If it were an unsigned number, this would simply be, value would simply be I equal to 1 to n minus 1 a I 2 power I, if it were unsigned. Correct? But if it is a signed number now, 2's complement representation is the following. I will write this as minus 2 power n minus 1 a n minus 1 plus summation I equal to 1 to n minus 2 a I 2 power I. Okay? So how do you identify now if this number is positive or negative? If I give you a 2's complement number, you look at the MSB. So if the MSB is 1, you are saying that the number has to be negative. How do you know? Yeah, in some sense, the maximum value of this guy is 2 power n minus 1 minus 1. This term is less than or equal to this. So what is the maximum value of that remaining part? Summation I, sorry, this is 0. 0 to n minus 2 ai. So let's look at that. I equals 0 to n minus 2 ai 2 power I. What is the maximum value? What configuration of bits of ai's will give you the maximum value? All ones, because it's all positive numbers, right? This is less than or equal to summation 2 power I, 0 to n minus 2. Therefore, this is less than, which is actually equal to 2 power n minus 1 minus 1, right? Now, clearly, if the MSB is 1, that is a n minus 1 is 1, then the number, right, is going to be minus 2 power n minus 1 plus 2 power n minus 1 minus 1. Therefore, if that MSB happens to be 1, then number has to be a negative number. It cannot be a positive number. Okay. So now if it is a negative number, what do you do in order to find out its value? Yeah? No, 2's complement representation is 1. What's the other thing that you do? You're taught an algorithm, right, of generating the value. Take complement of every bit. Take 1's complement and add 1 to it. We'll see why that has to be true. Okay. So now if a n minus 1 equal to 1, right, then the number is equal to 1's complement plus 1, and then you put a negative value of this. That's what they tell you, right? So for example, if I have a number 1101 and I tell you that this is a 2's complement number, first of all, what is the value of this number? Yeah? Minus 3. Yeah. Why is that? Because this is a 4-bit number, so this is minus 2 power 3, right? Let me write it here. Minus 2 power 3 plus 2 power 2 plus 0 plus 2 power 0, right? So which is equal to minus 3. Now what are we saying? If I want to, this is from the 2's complement evaluation. If I do the algorithm that I just told you, 1's complement, 1101, if I complement, I will get 0, 0, 1, 0. And then I add a 1, I will get 0, 0, 1, 1. Right? So the answer is minus of 3, negative of this number. Okay? So let's see formally why this thing has to be true. So if I take my n-bit number, which is in 2's complement form, a n minus 1, a n minus 2, all the way to a naught, right? And I just add it with a n minus 1 bar, a n minus 2 bar, all the way to a naught bar. What will this be equal to? 1, 1, 1, 1, 1. Every bit I am adding with its complement. Correct? So there can be no carry first of all. Because if this is 1, that will be 0. If this is 0, that will be 1. So this will be 1, 1, 1, 1, 1, all the way. And how many ones? N times. Right? Now what are we saying? A n minus 1, a n minus 2. This representation value is equal to 1, 1, 1, 1, 1 n times. What is that value? 2 power n minus 1, correct? Okay, no, wait, we'll come to that. We'll leave this as it is for now. Okay, minus bar a n minus 2 bar a naught bar. Correct? So now what have we done here? One, 1, 1 minus 1. First, what do we, okay, show that this number is a n minus 1 bar all the way to this, right? Sorry? No, 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 wait. So what do we want to do? We want to basically take the number, complement every bit, and then show that we have to add a 1, right? So this is nothing but 2 power n minus 1 this is going n times, right? What is this one here? This is nothing but actually the 111 minus the number itself, A3, A2, A1, A0. Correct? That is what it is. Then we are doing a plus 1, right? So what do you get? Why should you do that plus 1 is the question. Yeah. 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 Oh, you're saying that that value is nothing but minus 1 in 2's complement representation. 1's complement of that. Yes, that's right. So this is minus 1 minus an minus 1 complement, an minus 2 complement, a0 complement. So this is nothing but minus of 1 plus every bit complemented. So therefore this is a very consistent operation that you have been asked to do, and it will definitely work. Okay.